Hi there, and welcome back to the second video of the ECG part of our PPK 409 course. Today, I will explain you how we can create our own libraries with our self-written functions, and afterwards we'll go a little bit into how we can analyze the data that we've collected of our ECG. So we will talk about how we can find the heartbeat, so how we can find the R wave peaks of our ECG wave, how we can then calculate the heart rate, and then from there, how we can calculate heart rate variability and energy expenditure. First of all, I created my own folder in my working directory. So you can see my working directory here, and my folder is Lab 2 Patrick Meyerhofer. The working directory in that case would be desktop and then the Lab 2 Patrick Meyerhofer. So in this folder, we want to save our main codes where we have the main parts of our code. We want to save any libraries that we have self-written. I'll show you now how we can do this. We also want to save the library that we downloaded from GitHub. So in that case, the Lab 2 functions library. But we also want to save there all our data files that we need to import into our code to analyze the data afterwards. So for example, if I want to save this here as my main code now, let's save it here. We are in the right directory at Lab 2 Patrick Meyerhofer. Then let's call this as explained in the lab assignment. We call this main code 2, and it is 2 because we are working on Lab 2 right now. Main code 2, save this. If you can remember last time in our Lab 1, we imported some different libraries. Like for example, we imported pandas as, in that case, PD. So the pandas library gave us different functions that we could then use, like for example, the CSV import library. What we can do is we can also write a library like this by ourselves. And I want to show to you guys now how this works. So if we open a new file here, a new document, let's first save this here. For this here, let's just save it as try library. Let's save it like as try library. We also save it into the same folder as I explained before, and then we can write our first function. And by writing a function, if you want to write a function, you have to start with def. So that's you want to define the function. Let's call this a plus b. And then you have brackets. In the brackets, you will put the variables that you send into the function. I'll explain it in a moment. Then a column. And then if you click enter, you'll actually have an indentation here, which is very important because everything that is in this indentation column, so everything is a little bit more inwards than this here, means it will be what this function does. It will be in this function. So we can now, for example, say C equals A plus B, which means that for this here, we need to know what A and B is. So in our case, then we want to, the function has to get the values A and B. And then we want to return, this function should return the value for C. So now we can say return C. That's a whole function. So if you want to use this function now, first of all, as we did with the pandas, we need to import this library here. So for pandas, it's a little bit different because it's already saved on Python, so it does not have to be here. But if we write our own library, it needs to be in our working directory. And if we want to import this, then we can say import, since it's called try library, we import try library. Then we can also give it a name. So we say S, let's say TL in this case. And if we want to use this specific function of this library now, then we can say we first have to define two values. So let's say first value equals 1, second value equals 4. And then we can say, let's call it third value equals. And now we want to use the function from the try library function, the function from the try library. So we can then say TL dot, because we called it TL here. We can TL dot, and it's called A plus B. So A plus B, and then we have to tell it, because this function needs two values, we can tell it the two values that we want to send into this function, which in our case will be first value, second value. So if we run this file now, it will import our, this isn't important yet because we don't use it yet, but it will import the try library. It will create the first value and the second value, and then it will calculate the third value with this function here. So let's start it here. And there we go. We've created first and a second value, and then the third value was created by summing those two up because it does whatever this function tells it to do. So now if we want, for example, to have another function in here, we have to start from the very left indentation again. So then we say define a new function, and now let's say A divide B. And we again, let's just say we call them A and B. And then our C equals A divided by B. Then here we can then say return C and save this. So if we now want to divide here, we can say fourth value or whatever, doesn't matter, equals TL for the library, and then A divide B, A divide B, and then we needed to send two values. And let's, for example, now say, let's send it the third value and the, let's say the second value. And then we can either run the whole file again, or if we just want to run this one line, we can also click on it and then say run selection or current line. And there we go. Then our fourth value is 1.25 because it calculated the third value. So the third value was 5 divided by the second value, which was 4. So that's how we can create our own library and then our own functions within this library. I have now deleted everything in this code, and now we can talk about how we can analyze the data that we have collected before with our ECG microcontroller system. As you can see here in our working directory, I have added a few things. First of all, I have added the lab2 functions, which you can download from the GitHub repository, and where we have to use a few functions to analyze our data today. I've also added the lab2 resting data, so that's my ECG data from the resting experiment, and the lab2 exercising data, which is my data from the exercise experiment. I will not go too much into detail of this part of the code because we have learned this stuff in the last lab already. But let's just recall a few things. First of all, I'm importing a few libraries. Then I give the column names of the data that we're importing. I give the columns of the data that we're importing the names. So the first column is the ECG data, and the second column is the time of this data. And then we're importing this data. So since this file is already in our working directory, I can just call the name of the file. If we have this file saved somewhere else, then we also have to tell it the directory of this file. But for uploading it to our Canvas site, we would like you to put everything into the same folder, and there'll be explanation on the assignment that you'll use for every lab. When I import this data, I also skip a few rows. So since we have 1,000 hertz sampling frequency, I'm deleting 5,000 rows in the beginning of the file and 5,000 rows in the end of the file. So 5,000 rows means I'm deleting 5 seconds for each side. That's because I have to start the code, and then I'm lying down, and until I'm actually like lying and being still, there might have been 5 seconds of data collection. And in the end, the same, once the timer went off, you go up and then you disconnect the microcontroller and so on. And to be safe, I also delete 5 seconds in the end of the data. And then in the very end, I just change the time in milliseconds to seconds. I just had to minimize the window because otherwise you would see we would not see my plots afterwards when we're plotting. So let's now run this code here to import all the data. There we go. So we have now our resting ECG data frame. Let's have a look there. So here we have the ECG in the first column and the time in milliseconds in the second column. So now if we want to plot this data to just see how it looks like, and it's always a good idea to in the beginning just plot everything, just to get an idea of how the data actually looks like, we have to import our matplot library, and then we can say plt.plot resting ECG.time, so the time versus ECG versus the actual ECG data. We can now either run the whole file again or just this line to import the matplot library, and then we can run this line here to actually plot the data. There we go. You can't see anything here probably because it is there's a lot of data. So if we zoom in now, that's how the data looks like. So each peak here is actually the R wave peak that we want to search afterwards to find our heartbeat and our heart rate. Here is something else to mention. So as we have talked about in the lab manual, in this data, we have this super high frequency noise. This frequency is probably at around 60 Hertz. 60 Hertz because I guess my power was plugged into the power of the house, and the AC power line in North America works with 60 Hertz. So that's why if your computer is plugged in, you might actually get this noise here. And we've talked about this a little bit in the video before where we actually collected the data. To filter the data, we will first have to import the SciPy signal library. I'm not going to give it a special name right now, so we just import this here, and then we can filter the data. So first, as we already did in the video of the first lab before, we have to create our Butterworth filter, and we want the low frequencies to pass so that the high frequencies get cut out of the data. So, and then we have to talk a little bit about this critical frequency WN. So the critical frequency is a fraction of the Nyquist frequency. In our case, because we have collected our data with 1000 Hertz, the Nyquist frequency is 500, which means that if the critical frequency, let's say WN equals 1, if it's 1, then it's because the fraction of the Nyquist frequency of 500, then the cutoff frequency would be 500, which means that it would cut out all the frequencies that are higher than 500, which we don't really need. In our case, because we know that this noise we want to reduce is somewhere around 60 Hertz, a good idea would be to cut out all the frequencies that are higher than 50 Hertz, for example. So in this case, if we say now 500 Hertz, so if we take 0.1, so 0.1 times 500 is 50. So in that case, it will cut out all the frequencies. In that case, the cutoff frequency will be 50 Hertz. So it will cut out all the frequency that are over 50 Hertz, including the 60 Hertz noise, and it will let the frequencies under 50 Hertz pass. So let's just see if this works now. We will first have to import the SciPy signal here. And sorry, I can do it like this here. So import the SciPy signal here. And then we can define our WN. And then afterwards, we can, or let's just first create our filter. So we create a low pass filter with a cutoff frequency of 0.1 of the Nyquist frequency, which in our case will be 50. We have a fourth order filter. And there we go, we've created. And now with this line here, we're filtering the resting ECG signal. And if we filter this now, there we go. And now we can actually plot this again, plt.plot. Let's actually, to see the difference now, let's put this down here. Let's plot the original data first, and then the time with the filled resting ECG data. So if we run this now here, there we go. And if we zoom in here, that's now the difference. So the orange line here is the filtered data, and the blue line is the raw line. And one of the most important things for us here is we don't want to lose the characteristics of the data, but we also want to get rid of the noise here. So in that case, we still have like the structure and the characteristics of the actual data, but the noise is removed here. So this filter worked really well for us. Maybe let's have a look at this peak finder function first for a moment. If we want to find the peaks of the filtered ECG that we just saw, then we can use the function find peaks from the SciPy signal library. And we need the peaks, and because there is like a second output, we can just do a line here, which means that we don't really need this line, this variable, but we want to have the positions of the peak. So input for this function is our data, and the output is our peaks. So let's now run this part here. There we go. Okay, it created the peaks. And now if we want to have a look at this, we can create a figure and first plot our normal signal like this here. And then we can also plot the peaks that we just found. So that's with this here. So we can say it should just plot the, let's start here. It should just plot the data from the ECG where the peaks were found. And then obviously it also needs the time for this. So it's the same here. And it should just make an X here. So if I plot this here now, see here, there we go. Then the orange, then it makes an X everywhere where we just found a peak. And as I told you guys before, there will be a peak here, but then also because it's not perfectly filtered yet, there's like peaks here everywhere. But the only thing that we actually want is really just this peak up here. So there's another possibility that we can use here is we can say height equals, and I think 360 works well. And then we can just do the same here, create a figure. There we go. So now it creates a threshold at 360 and just finds the peaks on top of it. And that works pretty well with the resting ECG data. But I'm gonna show you guys something now, okay? So let's now import let's import the exercise data here. Import this here, or let's run this line here. And then, or let's do it down here. Let's plot it, plt.plot. Let's just see how this looks like. Exercise ECG.ECG. There we go. So now, if our data looks like this here, there will be almost no possibility for us to find there is no possibility for us to find a threshold that can just find these peaks here. So for this, we need now a special algorithm, and this algorithm is, we prepared this algorithm for you guys, and it's packed into the three functions, that you downloaded with the Lab2 functions library. I will just copy and paste everything here, and I'll explain it for you here now. So first of all, what I did, as I did before, I changed from milliseconds to seconds. And then I used 3 functions from the lab2 functions library that we provided to you on GitHub. So before we can start, we need to import this library. So I'm talking here about this, I'm talking here about this function, the lab2 functions library, and we need to import this as every other library too. So it's import lab2 functions, and I call it L2F just because that's short and easy. So now we can use this library and we can use its functions, those 3 functions. So what is this function doing now? So the first function changes or like calculates from the ECG data that we just saw. It calculates the derivative of this ECG data, and then it looks for the peaks in the derivative. Why do we do that? I'll just run this function and then you'll probably understand it a little bit better. So the input here is the normal ECG data and our time, and the output then is the derivative and all the peaks that it has found in the derivative of the ECG data. So let's run this line here. There we go. So if I zoom in here, as you can see now, the peaks are way more obvious in the derivative data than in the ECG data. So the peaks that you can see here are the peaks right before the R wave gets to its peaks, because that's where it rises the fastest, and that's exactly where the derivative is the highest. The problem here now is that we don't just want, that we do not just get the peaks that we want, we also as well get the peaks that we don't want. So for this, let's go back here. For this, we need to use the second function, because the second function now uses a threshold in height, but also a threshold for distance. So it tries to, we can decide on a distance, and the distance between each peak have to be at least this distance. And as an input, this function needs the derivative, then the peak, so it's the outputs from the functions before. It needs the time as well. And then here are 2 values that we can play around with those 2 values a little bit. The first value is for the height. It's not the actual height value, but it's a fraction. So like you can just like, it has to be between 0 and 1, and you can just play around with it and see what works best. And the second one is a fraction of the distance between those peaks. That's also between 0 and 1, and you can also play around here a little bit with it. Let's just have a look here now. Let's run this function. There we go. So the black line now shows us the threshold that it uses if you say 0.4 in our case. And let's go in here. And there we go. It actually worked really, really well. So now we just have the peaks on top. Let's not just see what happens if we change those values a little bit. Let's just say let's just change the fraction for the height. There we go. Then the threshold will be too low, and it will actually, give us too many peaks again. Let's change this back to 0.4. So 0.4 and 0.5 worked best for me. It might work best for you too. If it doesn't, then you can start to play around. But let's now see what happens if we say the fraction of the distance should just be 0.1. See here. There we go. So the threshold does not filter out this one here. And because the height threshold doesn't filter out this peak here, and because the distance is also so small, so like the minimum distance is very, very small, it also doesn't filter out it with this guy here with the distance. So if we change the distance fraction to 0.5, then this actually also filters out most of those ones. So now I think it was somewhere here. You see. Yeah, I can't find the exact one anymore. Oh, there we go. So here is one that is actually higher than the threshold, than the height threshold, but because of the distance threshold, it also filters out this peak here. If it doesn't work perfectly with 0.4 and 0.5 for you, you can play around with this. So now we have found the peaks for the derivative of the ECG, but what we actually want to find is the peaks of the R wave of the actual ECG. And this is what the last function here is for. The last function takes as an input our ECG data, the derivative of the ECG, then the peaks that we found in the function before, and the time here. So if we plot this here, here we go. So let's zoom in. Now we actually have the derivative and the ECG in one plot, and you can see really well here now that the ECG peak is right after the derivative peak, and that's the one that we want to look for. So the last function just looks for the peak in the ECG data right after the derivative peak. The output of this function now is what I called here the exercise R wave t. So that's the actual time of each heartbeat. So that's the time that we can use afterwards. So that's the time of the first peak, the second peak, the third peak, and so on. So with this time, we can then calculate the heart rate and the heart rate variability, but I'll go into this in a little bit. Before I go into this, I also want to mention something else. So in the beginning, we've worked with the resting ECG, and we had to filter the data from the resting ECG. But this data now was the exercise data, and this was the one that I collected not with the computer, but with the micro SD, and it has a way lower sampling frequency. So as you could see, and maybe I should plot this here. Maybe I should plot this here again. plt.plot. If I plot the raw exercise ECG.ECG and zoom in there, it is actually not as noisy. So if you look at your data before you start, you can then decide if you need to filter it or not. If the data looks like it looks here, then you don't need to filter it anymore because there is almost no noise in here anymore. So that wouldn't make any sense. Now we need to get from the times when all those R wave peaks happened to the heart rate in beats per minute. The first step for this is we need to calculate the RR interval. So the interval of the R wave peak. So that's the difference of the time of a beat minus when the beat before happened. And for this, I'll show you, let's call it RR interval. I will show you from the NumPy model, that diff function. So the diff function calculates the difference of one data point compared to the data point before. And we want to calculate the difference of exercise R wave t. And now we can actually plot this and just see how the difference looks like. Oh, I didn't run it yet. So I need to run this first. And then RR interval. Oh, I need to call it interval, not inverbal. Okay, there we go. That's a difference. So that's the RR interval. So the difference of each point compared to the one before. We have 4 outliers here. So this means that 4 times it did not detect a heartbeat in between. So that's why the difference is double the difference that it actually should be. But we'll filter the data later anyways. Our RR interval is basically the time constant between the heartbeats. So if you want to calculate the heart rate now, we basically just need to say 1 divided by the RR interval. So that's the sampling frequency then, but since the sampling the frequency is in seconds, we also need to calculate it times 60. And if we calculate times 60, then we are in minutes, which means now we are in beats per minute. And let's call this heart rate. Okay, run this here. And now we can plot it. Plot it. Here we go. So in this experiment, the subject had, here it was like 150 beats per minute, then it went down to 100 beats per minute, up to 160 beats per minute, down to 100 beats per minute, and so on and so on. From this here, you can then calculate the heart rate variability. This is not the case for the exercise experiment. You will actually do this for the resting experiment. I will put a link in this video, and there's also the link in the lab manual, which explains how you can calculate the heart rate variability. It doesn't explain how to do it in Python, but if you have the equation, you should actually be able at this point to figure out yourself how to put the equation into Python and calculate the heart rate variability with that. The same goes for the energy expenditure. After you have read the paper and decided on which energy expenditure model or equation you would like to use, you can use this function or this equation then in Python and calculate the energy expenditure. Maybe you would like to filter your heart rate data before a little bit, because the heart rate, as you have seen in the plots before, is a little bit noisy and might have 1 or 2 outliers. And if you filter it, it's a little bit more beautiful data and looks just a little bit better in a graph to analyze afterwards. And from this data, you will then be able to calculate the kilocalories and the joules that you have used in total in this exercise experiment. But this is also going to be explained in the lab manual, just if you need some guidance on that. With this, we're done with the Python video for today, or for this part of the course for the ECG. I hope that it helped you. We've talked a little bit about how to use or how to write your own libraries, your own functions, and then we went into using the functions that we've provided on GitHub to define the R wave peaks in the ECG, and afterwards how to calculate the heart rate from this, and from there you can then calculate energy expenditure and joules, kilocalories spent, and so on and so on. I hope that you'll enjoy this video. I hope it will help you to do all the things that you need to do. And with this, I'll see you soon. Bye-bye.